Okay, so here we have a velocity versus a time graph. Let's start thinking about all the information and where we can find the information on this graph. Okay, what kind of information can you find and where do you find it?
Where do you start?
Okay, this is a velocity graph. Where would you find where to start on? Where the person starts? Nope, what's on our y-axis? It's the speed, right? Not position. Okay, so if you've got, so that means that this cannot be position because it's actually velocity. Okay, so what does that tell us about, so that means we can find something on the y-axis. We can find the speed or the change in speed. Okay, we can find delta V, or we can just find the speed itself. What does just the speed itself tell you? That tells you one bit of information. It was very useful to know when you were doing your motion graphing. If you just know just the speed, what does that tell you about the scenario?
If it's increasing, decreasing, or if it's constant?
Nope. No, because actually for what you just said, increasing, decreasing, or staying the same, that's not telling you about the speed. That's telling you what the speed is doing. Does that make sense?
Yeah.
All right.
When you're going like towards and away
There
from,
you go. Good job. Go give yourself a point. Up front. Yeah. Okay. So if all you know is the speed itself, the speed or the velocity, then you know if it is plus or negative, you know whether you are moving away or toward. Okay. If you know two speeds or velocities, you know how things are changing. All right. So if it's delta V, you can know there's three things that you can know from the change. Up front, is that dead?
Yeah.
All right, to put it in the trash can as well. All right, what are the three types of changes you can find with the delta V? I'll give you a quick one. The first one is speed up. Slow down. What's the? No, that's not a change. Huh? Nope, that's not a change. Huh? What did you say? I want you to repeat it.
I was going to say direction, but it's not.
No, you're exactly right.
I'll let that and think of it.
Remember early on I said trust your darn brains? Okay? She's exactly right. Speed up, slow down, or turn around. That's what delta V will tell you. Okay? Can you kind of summarize why it's speed up, slow down, or turn around, or rather just why turn around is included?
turn around is when you're at the x-axis
Yeah.
and it hits that 0 point,
That's not
and
true.
when you're speeding up, it's going towards it, and you're slowing down, it's going away from
Not quite.
it. Or is it the other way?
Okay. Well, actually, the point I was trying to make was originally was that with delta V, velocity is a vector, and so vector is size and magnitude. So if you change the size, speed up or slow down, or you change the direction, which way you're going, any of those things is a change in velocity. I think you had your what was happening going back and forth. So that's our delta V. All right. Somebody mentioned slope. Okay. Now, we talked on Friday about what is it when slope of a velocity graph changes, or rather when velocity changes over a period of time. What is that called? Yeah, when you speed up, or you slow down, or you change direction, what's that called?
Acceleration?
Acceleration. Okay? All right, so when you change it over time, that's basically your slope. So that's what we find here. So if I were to divide velocity by time, okay, that's how I get acceleration. We can find the time on the x-axis. There's one more thing, there's one more place we can get information. Nope. I already circled the time on there. This was, we mentioned it briefly on Friday. It was part of your notes. What do you find? What's one more piece of information you can find? We haven't done any practice problems with it yet, but it's there. Also, add to your notes as we're talking through this, because I know we're expanding on some of the stuff we talked about on Friday. So if you need to add, add. There's one more piece of information. We've got the y-axis, we've got the x-axis, and we've got the slope. One more place. Look in your...
Is it the negative side of the graph?
Nope. Look in your notes underneath velocity. What's the last one? Huh? Okay, not that. Are you looking under the velocity notes? Okay.
Velocity graphs part?
Yeah.
How fast the train?
How fast, which way? What's the third one?
Oh, how fast? Determine which way you're above or below horizontal axis, and then do that.
Turn the page. Did we not finish our notes on Friday?
No.
That would be our problem. Okay, we are going to backtrack and let's put in this last thing. Here is number 3 to put onto your notes. All right. Whew.
This is being recorded.
Yes, it is. All right. Yeah. Pull up. Oopsies. We forgot the last little bit. That's actually very crucial to what we're talking about right now. So we can tell how fast by looking at the y-axis. We can tell which way. All right. We can tell if it's changing, and we can tell how far. Okay? You can tell how far by determining the area between the velocity graph and the horizontal axis. You can tell how far by determining the area between the velocity graph and the x-axis. So if I were to go ahead and figure out this area right here, that would tell me how far it traveled, something traveled over this space. So for example, all right, so and the variable that really describes how far something is, that's your delta x. That's your displacement. How far did it travel? That's a delta x. So if we want to find our area, it's the area of a triangle, so it's 1/2 base times height. Okay, equals 1/2. Our base is time. I'm sorry, our base is 5 seconds. Watch what happens with the units. Okay, that's the cool part. And our height is 20 meters per second. No, they cancel out, right? And what are we left with? Just meters. So that's how it works. That's why it works. It's because your units are canceling out. You're left with just meters. And this leaves us with 50 meters. So how far did the person go is 50 meters. And you can do this above the graph. You can do it below. We tend to call it the area under the curve. But the reality is it's between the curve and the axis. And by the way, a line is a curve. It's a special kind of curve. The same way a square is a special kind of a rectangle. Okay. So there's that. So let's go ahead and tell this as a story.
Determine.
Okay. All right. Could you tell where the story started on this one?
Stop.
Yeah. Well, we started at 0, 0, right? But does that tell us a position? No. All we can tell from this scenario is that from 0 to 5 seconds, you went 50 meters. That's all you can tell. You can tell delta x. You cannot tell final position. You cannot tell initial position. You can just tell what was the change. So there's our delta x. Let's go ahead and calculate our m really quick. Okay. So our slope is our acceleration, and which is going to be the change in velocity divided by the change in time. So our velocity was 20 minus 0, 5 minus 0, And that's going to give us, whoops, units, meters per second, divided by seconds. That gives us 4 meters per second squared. Yes, I know that we can go ahead and we can subtract for 0, and we can do that kind of in our head. We can definitely do that in our head. The reason why I wrote it out like this is I want to make sure that we understand that you have to have 2 points. All right? That acceleration, the same, is a slope. y2 minus y1, x2 minus x1. You have to have those 2 points. Okay? So now, could you please take this information, okay? If you take this information, and what is it? Was the area is our delta x, this is our 50 meters. We know that our slope, which is our acceleration, is equal to 4 meters per second squared. I would like for you, using whatever information is appropriate, turn this scenario into a linear equation. What is the physics equation for this scenario? You have all the information. Start with your y. When you're done, turn your board over so that I know you are done. Sorry if anybody who's listening here, we hit pause in the middle of the recording. Sorry. Okay, so y is velocity, our slope is 4 meters per second squared, x is t, do not forget to put that one in, and our y-intercept, in this case, is 0. Okay? Now, let's do another type of thing we can see with this. So in other words, if I asked you, said, hey, so here's a story. My kid's out walking the dog, okay? And at a certain point in time, the dog slips the leash because I have a 3-year-old, and the 3-year-old likes to yank on the dog's collar, so we don't want the dog to choke. So the dog slips the leash and takes off, all right? How fast is my kid going when he's 7 seconds away from home?
Yeah, the kid or dog? The kid, right?
The kid. The kid's doing the running. So how fast is my kid going? He would really love this because then he'd be the Flash. How fast would he be going at 7 seconds?
All the way over 7 seconds.
Huh?
Yeah.
That's the only thing I remember you saying is 7 seconds and the dog gets off the leash.
All right, so how fast is he going at 7 seconds? You have an equation. What is it?
Oh, we're following that.
Yeah, that's our story.
Oh.
Oh.
I thought you wanted us to say something else.
It's 28 meters, yeah.
Yeah.
Yeah, this is we're, because you don't always get just a graph. Sometimes you have the information you have to pull from it. So yeah, so if the dog breaks off the leash and takes a runner, and my kid's still running 7 seconds later at that particular acceleration, he's going 28 meters per second. Now let's add to that story. We're going to add to that story. So, my kid's out walking the dog. After a period of time, the dog slips the leash and does a runner. After 5 seconds, my kid is 60 meters from home. How far away was he when the dog slipped the leash?
Repeat that again, please.
All right. The kid, okay, they're out walking the dog. At a certain point in time, the dog slips the leash. The kid takes off running and catches him 5 seconds later. At 5 seconds later, he's 60 meters from home. How far away was he from home when the dog slipped the leash? Nope.
15 meters.
Look at the information we know. You know that he caught the dog at 60 meters.
No.
He caught the dog at 60 meters. So what does that tell you? That is his final position, right? Okay, so we know that X is 60. All right, I want to know, where was he when he started running? Where was he when the dog slipped the leash? Okay. What else do we need to know for this? It's on the board. Yep, but hey, even simpler than that. Do we know how far he went the entire time?
20 meters.
4 meters per second.
Take a look. Yes, we do. Delta X. We know how far he ran.
Oh, 50 meters.
50 meters, right? So we know our delta X is 50 meters. So how far away was he from home?
10.
10. Okay. Yeah. Yeah. Every number but 10 was that. But that's okay. But that's what I'm trying to get you. You can only know how far away something is. You could figure out the initial or the final, but they have to give you a little bit more. They have to tell you a little bit more in the story, okay? All right. That was example 1.